And now let's do one learning rate decay. What this means is we're going to take our learning rate and we're going to 10x lower it. And so we're at the late stages of training potentially, and we may want to go a bit slower. Let's do one more actually at 0.1, just to see if we're making a dent here. Okay, we're still making dent. And by the way, the bigram loss that we achieved last video was 2.45. So we've already surpassed the bigram model. And once I get a sense that this is actually kind of starting to plateau off, people like to do, as I mentioned, this learning rate decay. So let's try to decay the loss, the learning rate, I mean. And we achieve it about 2.3 now. Obviously, this is janky and not exactly how you would train it in production, but this is roughly what you're going through. You first find a decent learning rate using the approach that I showed you. Then you start with that learning rate and you train for a while. And then at the end, people like to do a learning rate decay, where you decay the learning rate by, say, a factor of 10, and you do a few more steps, and then you get a trained network, roughly speaking. So we've achieved 2.3 and dramatically improved on the bigram language model using this simple neural net as described here, using these 3,400 parameters. Now there's something we have to be careful with. I said that we have a better model because we are achieving a lower loss, 2.3.
I just wanna see how much. Okay, I did it on a different system altogether. Not sure how much I was achieving there, but anyway.
Much lower than 2.45 with the bigram model previously. Now that's not exactly true. And the reason that's not true, the bigram, because we are achieving a lower loss, 2.3, much lower than 2.45 with the bigram model previously. Now that's not exactly true. And the reason that's not true is that this is actually a fairly small model, but these models can get larger and larger if you keep adding neurons and parameters. So you can imagine that we don't potentially have 1,000 parameters, we could have 10,000 or 100,000 or millions of parameters. And as the capacity of the neural network grows, it becomes more and more capable of overfitting your training set. What that means is that the loss on the training set, on the data that you're training on, will become very, very low as 0. But all that the model is doing is memorizing your training set verbatim. So if you take that model and it looks like it's working really well, but you try to sample from it, you will basically only get examples exactly as they are in the training set. You won't get any new data. In addition to that, if you try to evaluate the loss on some withheld names or other words, you will actually see that the loss on those can be very high. And so basically it's not a good model. So the standard in the field is to split up your dataset into 3 splits, as we call it.
So this is a general machine learning problem. So what he's saying is, I think there was a problem where when we start with machine learning, right? Classical machine learning is predicting the price of a house based on different features of that house, means number of bedrooms, washrooms, dimension of the house and everything. These are different features. So what used to happen, so if you take all of that data and train the model and reduce the loss, is what he's saying, right, to 0 or very close to 0, right? What that means is it has overfitted that model. It means if you show any new data or something like that, right, the errors will be pretty high because it has put a lot of effort to learn just those training data. Means it has overfitted, means it has, means kind of a rule based, you can say this is this, this is this is something like this, which might not generalize well. So where we want to reach is where it learns something from the training data that we have given, but generalized as well, so that it works with new data as well. That's the intention. Okay. So you can think of an example, something like a chat GPT or something like that, right? So if you train it um, so much on just Wikipedia, 2 3 pages, right, and expect it to work for a general public asking question, it won't happen. It's anyway, general public might be very tough because they can ask any questions, but if you train it on just the Wikipedia data, right, it will just know that part of data. And if you overfit, right, if you ask it anything apart from the thing that is not there in the Wikipedia, but you expect a normal human being to go through Wikipedia pages and able to answer, right? That's the expectation, that if an individual, right, if I give you 20 Wikipedia pages and then try to ask questions, right, which is not completely from those, but you can still make out. It's, that's the intention. So the expectation is we should not overfit, and how we do that is we split the data into 3 parts. That's what
We call them.
we say.
We have the training split, the dev split or the validation split, and the test split. So training split, dev or validation split, and test split. And typically this would be, say, 80% of your data set, this could be 10%, and this 10% roughly. So you have these three splits of the data. Now these 80% of your trainings of the data set, the training set, is used to optimize the parameters of the model, just like we're doing here, using gradient descent. These 10% of the examples, the dev or validation split, they're used for development over all the hyperparameters of your model. So hyperparameters are, for example, the size of this hidden layer. Hyperparameters, the dev or validation split, they're used for development over all the hyperparameters of your model. So hyperparameters are, for example, the size of this hidden layer, the size of the embedding. So this is 100 or a 2 for us, but we could try different things. The strength of the regularization, which we aren't using yet so far. So there's lots of different hyperparameters and settings that go into defining a neural net, and you can try many different variations of them and see whichever one works best on your validation split. So this is used to train the parameters, this is used to train the hyperparameters, and test split is used to evaluate basically the performance of the model at the end. So we're only evaluating the loss on the test split very, very sparingly and very few times, because every single time you evaluate your test loss and you learn something from it, you are basically starting to also train on the test split. So you are only allowed to test the loss on the test set very, very few times. Otherwise, you risk overfitting to it as well as you. Experiment on your model. So let's also split up our training data into train, dev, and test. And then we are going to train on train and only evaluate on test very, very sparingly. Okay, so here we go. Here is where we took all the words and put them into X and Y tensors. So instead, let me create a new cell here and let me just copy paste some code here because I don't think it's that complex, but we're going to try to save a little bit of time. I'm converting this to be a function now. And this function takes some list of words and builds the arrays x and y for those words only.
So what it is doing is length of words. Say there are 10 words. He's taking 8 words, putting it into N1. So from starting till 8, it is taking those all those words. 8 words it is taking. Then he's going from 8 to 9, and then 9 afterwards is done by this. So 1,82,000, 22,000, 22,000. So anyway, this is I think the maximum, where was it of this? So this is, so you see approximately like that. I think it doesn't make sense. What do 814? What do 814? Anyway,
And then here, I am shuffling up all the words. So these are the input words that we get. We are randomly shuffling them all up. And then we're going to set N1 to be the number of examples that is 80% of the words, and N2 to be 90% of the way of the words. So basically, if length of words is 32,000, N1 is, well, sorry, I should probably. And so here we see that I'm calling build dataset to build a training set X and Y by indexing into up to N1. So we're going to have only 20, roughly N2 minus N1, 3,000 validation examples or dev examples. And we're going to have len of word 4 examples here for the test set. So now we have X's and Y's for all those three splits. Oh yeah, I'm printing their size here inside the function as well. But here we don't have words, but these are already the individual examples made from those words. So let's now scroll down here. And the data set now for training is more like this. And then when we reset the network, when we're training, we're only going to be training using X train, and Y train. So that's the only thing we're training on. Let's see where we are on the single batch. Let's now train maybe a few more steps. Training of neural networks can take a while. Usually you don't do it inline. You launch a bunch of jobs and you wait for them to finish. Can take multiple days and so on. Luckily, this is a very small network. Okay, so the loss is pretty good. Oh, we accidentally used a learning rate that is way too low. So let me actually come back. We used
so we will just train on the training set. takes some time.
The decay learning rate of 0.01. So this will train much faster. And then here, when we evaluate, let's use the dev set here. Xdev and ydev.
What is the loss we are getting?
To evaluate the loss. Okay. And let's now decay the learning rate and only do, say, 10,000 examples. And let's evaluate the dev loss once here. Okay, so we're getting about 2.3 on dev. And so the neural network, when it was training, did not see these dev examples. It hasn't optimized on them. And yet, when we evaluate the loss on these dev, we actually get a pretty decent loss. And so we can also look at what the loss is on all of training set. Oops. And so we see that the training and the dev loss are about equal. So we're not overfitting. This model is not powerful enough to just be purely memorizing the data. And so far, we are what's called underfitting, because the training loss and the dev or test losses are roughly equal. So what that typically means is that our network is very tiny, very small. And we expect to make performance improvements by scaling up the size of this neural network.
We get the training loss equal to dev loss. Two point 2.40. That was on that batch, right? This, whatever this value we are getting on this 32 batch, on the whole of the training, how it will be somewhat nearer.
So let's do that now. So let's come over here and let's increase the size of the neural net. The easiest way to do this is we can come here to the hidden layer, which currently has 100 neurons, and let's just bump this up. So let's do 300 neurons. And then this is also 300 biases. And here we have 300 inputs into the final layer. So let's initialize our neural net. We now have 10,000 parameters instead of 3,000 parameters.
What became a tensor object? Okay. It's okay. Sorry, we haven't initialized this. So previously it was 4,000. Now it is 12,000. Usage analytics.
And then we're not using this. And then here what I'd like to do is I'd like to actually keep track of that. Okay, let's just do this. Let's keep stats again. And here when we're keeping track of the loss, let's just also keep track of the steps. And let's just have I here. And let's train on 30,000, or rather say, okay, let's try 30,000. And we are at 0.1, and we should be able to run this and optimize the neural net. And then here, basically, I want to plt.plot the steps against the loss. So these are the x's and the y's, and this is the loss function and how it's being optimized. Now, you see that there's quite a bit of thickness to this, and that's because we are optimizing over these mini batches, and the mini batches create a little bit of noise in this. Where are we in the def set? We are at 2.5, so we still haven't optimized this neural net very well. And that's probably because we made it bigger. It might take longer for this neural net to converge. And so let's continue training. Yeah, let's just continue training.
weights.
One possibility is that the batch size is so low that we just have way too much noise in the training. And we may want to increase the batch size so that we have a bit more correct gradient and we're not thrashing too much. And we can actually optimize more properly. Okay. This will now become meaningless because we've reinitialized these. So yeah, this looks not pleasing right now. But there probably is a tiny improvement, but it's so hard to tell. Let's go again. 2.52. Let's try to decrease the learning rate by a factor of 2. Model, and we were underfitting, so we were lost than what we had. We basically expect to see a lower loss than what we had before, because now we have a much bigger model, and we were underfitting. So we'd expect that increasing the size of the model should help the neural net. 2.32. Okay, so that's not happening too well. Now, one other concern is that even though we've made the 10H layer here, or the hidden layer much bigger, it could be that the bottleneck of the network right now are these embeddings that are two-dimensional. It can be that we're just cramming way too many characters into just 2 dimensions, and the neural net is not able to really use that space effectively, and that is sort of the bottleneck to our network's performance. Okay, 2.23, so just by decreasing the learning rate, I was able to make quite a bit of progress. Let's run this one more time. And then evaluate the training and the dev loss. The embedding vectors for these characters before we scale up the embedding size from 2, because we'd like to make this bottleneck potentially go away. But once I make this greater than 2, we won't be able to visualize them. So here, okay, we're at 2.23 and 2.24, so we're not improving much more, and maybe the bottleneck now is the character embedding size, which is 2. So here I have a bunch of code that will create a figure, and then we're going to visualize the embeddings that were trained by the neural net on these characters. Because right now the embedding size is just 2, so we can visualize all the characters with the x and the y coordinates as the 2 embedding locations for each of these characters. And so here are the x coordinates and the y coordinates, which are the columns of C, and then For each one, I also include the text of the little character. So here what we see is actually kind of interesting. The network has basically learned to separate out the characters and cluster them a little bit. So for example, you see how the vowels A, E, I, O, U are clustered up here. So
XQR.
what that's telling us is that the neural net treats these as very similar, right? Because when they feed into the neural net, the embedding for all of these characters is very similar. And so the neural net thinks that they're very similar and kind of like interchangeable, if that makes sense. Then the points that are like really far away are, for example, Q. Q is kind of treated as an exception, and Q has a very special embedding vector, so to speak. Similarly, dot, which is a special character, is all the way out here. And a lot of the other letters are sort of like clustered up here. And so it's kind of interesting that there's a little bit of structure here after the training, and it's definitely not random, and these embeddings make sense. So we're now going to scale up the embedding size and won't be able to visualize it directly, but we expect that because we're underfitting and we made this layer much bigger and did not sufficiently improve the loss, we're thinking that the constraint to better performance right now could be these embedding vectors. So let's make them bigger. Okay, so let's scroll up here. And now we don't have two-dimensional embeddings. We are going to have, say, 10-dimensional embeddings. For each word. Then this layer will receive 3 times 10, so 30 inputs will go into the hidden layer. Let's also make the hidden layer a bit smaller. So instead of 300, let's just do 200 neurons in that hidden layer. So now the total number of elements will be slightly bigger at 11,000. And then here we have to be a bit careful because, okay, the learning rate we set to 0.1. Here we are hard coding 6. And obviously if you're working in production, you don't want to be hard coding magic numbers. But instead of 6, this should now be 30. And let's run for 50,000 iterations, and let me split out the initialization here outside so that when we run this cell multiple times, it's not going to wipe out our loss. In addition to that, here, let's, instead of logging loss.item, let's actually log the, let's do log 10. I believe that's a function of the loss. And I'll show you why in a second. Let's optimize this. In production, you don't want to be hard coding magic numbers, but instead of 6, this should now be 30. And let's run for 50,000 iterations, and let me split out the initialization here outside, so that when we run this cell multiple times, it's not going to wipe out our loss. In addition to that, here, let's, instead of logging loss.item, let's actually log the, let's do log 10. I believe that's a function of the loss. And I'll show you. show you why in a second. Let's optimize this. Basically, I'd like to plot the log loss instead of the loss, because when you plot the loss, many times it can have this hockey stick appearance, and log squashes it in. So it just kind of like looks nicer. So the x-axis is step I, and the y-axis will be the loss I. And then here, this is 30. Ideally, we wouldn't be hard-coding these. Okay, so let's look at the loss. Okay, it's again very thick because the mini batch size is very small, but the total loss over the training set is 2.3, and the tests or the def set is 2.38 as well. So far so good. Let's try to now decrease the learning rate by a factor of 10 and train for another 50,000 iterations. But again, we're just kind of like doing this very haphazardly, so I don't actually have confidence that our learning rate is set very well, that our learning rate decay, which we just do at random, is set very well. And so the optimization here is kind of suspect, to be honest. And this is not how you would do it typically in production. In production, you would create parameters or hyperparameters out of all these settings, and then you would run lots of experiments and see whichever ones are working well for you. Okay, so we have 2.17 now and 2.2. Okay, so you see how the training and the validation performance are starting to slightly slowly depart. So maybe we're getting the sense that the neural net is getting good enough, or that number of parameters is large enough that we are slowly starting to overfit. Let's maybe run one more iteration of this. You would be running lots of experiments, and then you are slowly scrutinizing whichever ones give you the best def performance. And then once you find all the hyperparameters that make your def performance good, you take that model and you evaluate the test set performance a single time. And that's the number that you report in your paper or wherever else you want to talk about a single time. Make your def performance good. You take that model. Once you find all the hyperparameters that make your def performance good, you take that model and you evaluate the test set performance a single time. And that's the number that you report in your paper or wherever else you want to talk about and brag about your model. So let's then rerun the plot and rerun the train and dev, holding us back very likely. It is the case that the embedding size of these was holding us back very likely. Okay, so 2.16, 2.19 is what we're roughly getting. So there's many ways to go from many ways to go from here. We can continue tuning the optimization. We can continue, for example, playing with the size of the neural net, or we can increase the number of words or characters in our case that we are taking as an input. So instead of just 3 characters, we could be taking more characters. That as an input, and that could further improve the loss. Okay, so I changed the code slightly. So we have here 200,000 steps of the optimization, and in the first 100,000 we're using a learning rate of 0.1, and then in the next 100,000 we're using a learning rate of 0.01. This is the loss that I achieve, and these are the performance on the training and validation loss. And in particular, the best validation loss I've been able to obtain in the last 30 minutes or so is 2.17. So now I invite you to beat this number, and you have quite a few knobs available to you to, I think, surpass this number. So number 1, you can of course change the number of neurons in the hidden layer of this model. You can change the dimensionality of the embedding lookup table. You can change the number of characters that are feeding in as an input, as the context into this model. And then of course you can change the details of the optimization. How long are we running? What is the learning rate? How does it change over time? How does it decay? You can change the batch size, and you may be able to actually achieve a much better convergence speed in terms of how many seconds or minutes it takes to train the model and get your result in terms of really good loss. And then of course, I actually invite you to read this paper. It is 19 pages, but at this point you should actually be able to read a good chunk of this paper and understand pretty good chunks of it. And this paper also has quite a few ideas for improvements that you can play with. So all of those are knobs available to you, and you should be able to beat this number. I'm leaving that as an exercise to the reader, and that's it for now, and I'll see you next time. Before we wrap up, I also wanted to show how you would sample from the model. So we're going to generate 20 samples. At first, we begin with all dots, so that's the context. And then until we generate the 0th character again, we're going to embed the current context using the embedding table C. Now, usually here, the first dimension was the size of the training set, but here we're only working with a single example that we're generating.